This is a walkthrough of Problem 1 on Exam 1 of Module 7 in the book Problem Solving Guide for Electromagnetism and Optics. Many applications, an ion beam is needed in which all the ions have the same velocity. To accomplish this, a velocity selector can be used. Here is a diagram of a velocity selector. We are looking down the barrel of the gun. The ions are shot into the page, and this one has a magnetic field that's upward. Part A asks, if positive ions with a given speed are to be undeflected, what is the direction of the electric field? So if we put our thumb into the page and our fingers pointing upward, our palm is facing to the right. That is the direction of V cross B. The charge is positive, so the direction of the force is in the direction of V cross B. The magnetic force is to the right on a positive particle moving into the page. In order to work as a velocity selector, the electric force must be to the left. It's a positive particle, so that means the electric field must be to the left. And there it is. Electric field is to the left. The B field is upward. Part B. If negative ions with the given speed are to be undeflected, what is the direction of the electric field? So now we're shooting negative ions down the barrel. The B field is upward. With the negative ion, the direction of V cross B is the same. V is into the page, B is up, which means V cross B is to the right, but the charge is negative. So the direction of the magnetic force is to the left. If it's going to work as a velocity selector, the electric force must be to the right. However, the charge is negative. If the charge is negative, the electric field must be to the left, as shown in the diagram. So it's the same as part A. In order to work as a velocity selector, the electric field is to the left for both negative and positive ions. Part C. The velocity selector is tuned for ions moving at 400,000 meters per second. Which way is the deflection of a negative ion moving at 500,000 meters per second? We have to look at the forces. With a negative ion, the direction of the magnetic force is to the left, and the electric force is to the right. Let's put that on the diagram. If it's going too fast, the magnetic force is too big. The electric force doesn't change if it's moving faster. The magnetic force grows if it's moving faster. So the particle's going too fast, it gets deflected in the direction of the magnetic force, which is to the left. Part D, with a positive ion, you shoot a positive ion down the barrel, it's going too fast. The direction of the magnetic force is to the right, and the direction of the electric force is to the left. It's the opposite. Again, it's going too fast. Again, it deflects in the direction of the magnetic field, but this time the magnetic field is to the right, so it deflects to the right. Finally, part E, if the selector has a magnetic field of 2 Tesla and is tuned for alpha particles moving at 500,000 meters per second, what is the magnitude of the electric field? Well, a velocity selector is just the balance of the electric and magnetic forces. So the electric force is QE, the magnetic force is QVB. The Q's cancel, so the charge on the ion is irrelevant. There is no M in there anywhere. The mass is irrelevant. The speed is E over B. The selection speed is E over B, and we have the speed, and we have the magnetic field. We have to calculate the electric field. Plug in the numbers, and we get 1,000,000 volts per meter, or 1,000,000 newtons per coulomb. That's problem 1.